Let's begin chapter 1 of CHE 111 with regards to our lecture notes. The first chapter is very much an introductory chapter, so it does not go into the meat or the heart of chemistry. So a couple of goals of this chapter. We will first begin with a discussion of a definition of chemistry. Why are we taking this class? And why is it important to take this class? A couple of introductory terms and preliminary definitions. We'll go into a discussion of significant digits. And then we will talk about accuracy versus precision, know some of the differences between the two and their definitions. And probably the most important thing that you will probably need to take from this entire chapter in terms of importance and how it will forbear towards the later chapters is this last bullet point, the fifth one, units and unit conversion. So this one will probably, if you have a good understanding of this, specifically relationships and how to convert from one unit to another unit to understand this idea of dimensional analysis, I really believe mastery of this fifth bullet point will really give you mastery throughout the entire course. And if you don't understand this fifth bullet point, you'll have plenty of practice later on. So a lot to go over here. Let's first discuss the definition of chemistry. So no matter what level of science that you have undertaken, whether it's just high school or whether you've taken several chemistry courses or science courses for that matter, we all begin in chemistry with sort of splitting things. And the first chemists split matter, which is really anything that has space and has a mass. And they have split matter into the fundamental components of solids, liquids, and gases. But you can do a further split of solids, liquids, and gases and take a look at the molecules and compounds that comprise the solids, liquids, and gases. And then the split can continue further because these molecules and compounds that comprise the three fundamental states of matter are actually themselves composed of elements and atoms. And then finally, you can parse this out into something that's entirely invisible. That is the atom, which is split up into protons and neutrons and electrons. So in terms of detection, we can really detect solids, liquids, and gases. And by that, I mean we can describe a solid by properties. It's hard, or it could be soft, it could be pliable, it could be malleable, it could conduct electricity. In terms of liquids, we can describe them as how viscous they are, in terms of their color, their resistance, or their ability to flow. And gases, we can really describe them in terms of odor, perhaps. We can describe them in terms of mass. But the bottom line is that our senses, whether it's taste, whether it's touch, whether it's eyes, whether it's feelings, excuse me, whether it's odor, we can really describe matter in a macroscopic sense. But then as we go finer and finer into detail, we lose some of that ability for description. Submicroscopic is how I define these finer and finer details of matter, because we really can't see these under a microscope. And then we have the subatomic world, protons, neutrons, and electrons. This is something that has its own math, the math of quantum mechanics, quantum physics. That's how we describe their behavior, the subatomic world. There's a chapter where we just deal with electrons and their capabilities and their behaviors. So these we really cannot describe in terms of behavior, but I can say in the subatomic world we can detect them. So detection is where we really go about talking or describing these two worlds, whereas our five senses is how we describe matter. So then again, when we split everything into finer and finer details, the question comes, what is chemistry? So chemistry really involves a transformation. So whether you're talking about the level of matter at this level, the transformations in going from solids to liquids or liquids to gases, vice versa, or solids to gases. The transformations that undergo or undergone between molecules and compounds, the rearrangements of elements and atoms, the transformations that occur at this level, the release or the abstraction of protons, the release or the abstraction and taking of electrons. All of these transformations, no matter at what level of order or what level of detail you want to describe them, really is chemistry in a nutshell. And of course, chemistry branches out because you have finer subdisciplines in chemistry, like physical chemistry, organic chemistry, and biochemistry. So chemistry, as how I like to define it, is really the study of these transformations, detailing and documenting these transformations that occur at matter, which is sort of at the physical macroscopic world, or the transformations that occur at the submicroscopic and subatomic world. Remember, these we can't really detect. We really can't use our five senses to really understand or grasp. We really look at their detection using instrumentation and whatnot. So chemistry is really detailing transformations of states of matter at any of these levels of detail or magnification. So the question may be asked is, how do we describe these transformations that underlie chemistry? Well, there's two ways. One is we see and visually observe what is the reaction or what is the chemical or what is the element. We observe them, and those observations, usually we write these down in a lab notebook or we make some sort of documentation or recording of them, but these observations can be qualitative in nature. In this, we think of qualitative descriptions as sort of visual identifiers or as descriptors. So for example, sodium chloride is a white crystalline solid. That would be a qualitative observation of sodium chloride. That is what we observe, and that is what we write or record if we were given a sample of sodium chloride. Or for example, iron is a brown rust-like appearance. So that is a qualitative observation for iron. So like that, you can describe what we see in terms of visual descriptors. We can also describe and record what we see quantitatively, and usually quantitatively as derived from the word quantity has some sort of number affixed to that particular observation. So for example, sodium chloride is white crystalline. That is a qualitative observation that I just note. But if I want to go further in my observation, I can state that sodium chloride, 1 mole of that has 58 or so grams. So by introducing a number to that observation, I have made a quantitative description. The density of water is 1 gram per mil at 25 degrees C. So that is a quantitative description in terms of me describing a certain property of water. Another way we can document or understand these transformations is by not just recording what we see, and also what we smell, or if there's any heat, or if there's any type of color change. But a lot of the chemicals or chemistry in general relies upon us to understand properties. So properties are sort of innate to the system. So as an example, a property of me would be that I have black hair. I was just born with that property of having black hair. We subdivide properties as those that are being chemical in nature. So chemical properties are those that underscore any type of reactivity that's intrinsic to them. So as an example, the sugar glucose reacts with the sugar glucose reacts with oxygen to yield carbon dioxide and water. So that is a combustion reaction. I've just described a chemical property of the sugar glucose. Coming back to the example of sodium chloride, a chemical property of sodium chloride would be perhaps that it's completely soluble in water. So I've described a solubility property of sodium chloride, and that's some sort of chemical nature to it. The element sodium, when it burns in a flame, yields a very bright, maybe orange-greenish color. So that's a chemical property of the element sodium. In fact, all elements of the periodic table have some sort of chemical property when you put them close to a flame. So chemical property as a type of property deals with reactivity. Then we have physical properties. So this is sort of innate to the material or to the system. Physical properties, again, can be qualitative or they can be quantitative. Melting point and boiling point are very, very classical examples of physical properties. So the boiling point of water, 100 degrees C. Water is colorless and has a very low viscosity. All of those are physical properties. Water was quote unquote born with those physical properties. Now remember, I'm not talking about any chemical reactivity, whether water or any other chemical reacts with one other substance or another substance. That would be a chemical property. Here we're dealing with properties that are sort of innate to the chemical material or whatever system you're talking about. Extensive properties are properties that depend on the amount of matter you have, and intensive properties are properties that do not depend on the amount of matter you have. And in our lecture notes that we will go over, we'll give you some examples of extensive and intensive properties. I just want to give you a teaser about what's to come in the rest of this course. This idea of relationships or conversion factors is going to be very critical. And once you master this, you will really become an expert in one aspect and one field of chemistry, and it will make actually the course much, much easier. So just to begin, I want to start off easy. We know that 1 dozen is equal to 12 eggs, or 1 dozen is equal to 12 donuts. In fact, 1 dozen of anything is equal to 12 of anything. This represents a equivalence. It's unequivocal and it is definite. So 1 dozen does not equal to 12.1 eggs, and 1 dozen eggs does not equal to 12.2 or 11.9 eggs. It's 1 dozen equals to 12 eggs and 12 eggs exact. So this is what we'll call a conversion factor, because it helps us convert any types of eggs to any dozen, or any dozen to any number of eggs. And notice with conversion factors and these types of relationships, I could have the 1 dozen in the numerator and the 12 eggs in the denominator, as seen here. I can also flip it. I can have the 12 eggs in the numerator and the 1 dozen in the denominator. It will still reflect the same equivalence. $1 is equal to 4 quarters. So that is another conversion factor that expresses the relationship between a dollar and quarters. And notice the power of this relationship. If I have 10 quarters, I should be able to convert that to dollars using this conversion factor. If I have $5, I should be able to tell using this relationship how many quarters there are in those $5. Here's another example. 1 mile is 5,280 feet. So that is invariant, that is equal, and that is unequivocal. I could also just as well have my 5,280 feet in the numerator and my 1 mile in the denominator. It doesn't matter. It will still express that same equivalence. 1 meter is 100 centimeters. So these last two conversion factors actually represent conversions in distance. This second one represents conversions in currency. This first conversion factor represents conversions in terms of quantity. In this case, quantity of eggs, or it could be quantity of donuts, or quantity of whatever item. All of these are relationships. So learning chemistry means learning relationships. Here's a relationship that you will soon learn. It's 1 mole. We haven't talked about this concept of the mole, but 1 mole of CO2 is about 44.01 grams of CO2. So that is a relationship that expresses how many grams of CO2 are in 1 mole of CO2. Another relationship. 1 mole of carbon, the C represents the element carbon, contains this many atoms of carbon. That's a lot, 6.022 times 10 to the 23 atoms of carbon. So these are relationships that are probably something that you don't know because you haven't taken a chemistry class, while the relationships above are relationships or conversions that you possibly do know just by living everyday life. Big picture mentality framework, understand relationships, and if you learn these relationships and when and how to use them, the course will become much, much more easier. All right, everyone, let's go over Chapter 1 notes. Don't forget to do these homework problems and check your answers with those in the back of the book, and turn them in at the due date specified in the syllabus to get your 10 points. Just something to help you with the future, specifically with regards to nomenclature and how to name some of these chemicals and compounds that you will use, especially when you take Chem 2, when we actually work with some of these chemicals. I'd like for you to make flashcards of Table 3.2, Table 3.3, and Table 3.4. Make sure you memorize those. However, for the exam, I will let you use your flashcards for consultation. So as we begin, just as a refresher from what was depicted and talked about in the PowerPoint slide that was at the beginning of this lecture, chemistry is the study of matter, specifically its transformations. We could have transformations from solids, liquids to gases. We could have transformations from molecules and compounds. And we can have transformations that occur within elements as they react to other elements. And we can have transformations at the level of protons exchanging or electrons exchanging. So reactivity at all levels and all magnifications of matter is chemistry. So briefly talking about the scientific method, I'm going to go through this very fast because number one, it's really not the heart and soul of chemistry, and we really want to talk about the heart and soul of chemistry. And number two, you probably can get a lot of this stuff in other types of beginning science classes or a beginning biology class. So quantitative and qualitative explanations. We've talked a little bit about this in the PowerPoint beginning. That prelude talks about how qualitative explanations are those explanations that describe some sort of visual aspect to how you're wanting to describe things. Remember, observations. We are investigators. We are detectives. We need to record things. We need to write things down. How do we do that? We do that in the language of chemistry by describing qualitative behavior or quantitative behavior. Numbers, density is a quantitative apt descriptor. Melting point, boiling point, those are quantitative descriptors of what we're trying to explain. The idea of a hypothesis is that it's testable. It can also be false. So once it's false, then we have to take our observations, we have to take our statements and revise it. Law, a scientific statement that is true. So examples of laws include E equals mc squared, that equation. Force is equal to mass times accelerations. Those are mathematical laws. Some laws can be more verbal. Dalton's law of multiple proportions. By Dalton says that when two elements combine, they form a compound. They do so in simple ratios. That means CO2 is CO2, one carbon and two oxygens. It's not C2.3O 4.8. Okay, it's one atom of C, two atoms of oxygens. Finally, we have a theory, which is an all-unifying principle. Einstein's theory of relativity, Dalton's theory of the atom are two examples of theories. So one of my students last year confronted me about the differences between a law and a theory, but he was saying some theories can be laws and laws can be theories. I'm not going to go into all of that type of level of minutia and detail. Just hold what we see as these definitions. A law is a scientific statement that is true, and a theory is just an all-unifying principle that is one step higher than a law. So a law is true, and if a law undergoes much, much more vigor, then it can graduate into a theory. I'm not going to really test you on differences between a law and a theory. I put this little flow chart in here, classifications of matter. People have divided essentially into invisibility. So this flow chart is another one of those divisions. And it's important because it talks about some of the things that we'll be discussing. This idea of matter is anything that has space, anything that has mass and occupies space. But matter can be a mixture or a substance. Mixtures can be split up into homogeneous or heterogeneous. Classic example of a homogeneous mixture would be sodium chloride dissolved in salt. You would not know sodium chloride is dissolved in salt until you drank it and found out that it had a salty taste to it. So a lot of things are homogeneous. That is, they are just in one solution. The solute is completely mixable and miscible in the solvent. So that would be a homogeneous mixture. A heterogeneous mixture would be your classic oil and water. So those things are immiscible or cannot mix. So they actually partition into phases. For those of you that have more molecular biology or biochemical, phenol and chloroform. phenylchloroform, separate. No matter how much you shake, you cannot get those two to mix, and they'll always split. You'll have the phenol layer on top and then the chloroform layer at the bottom. So anyways, mixtures are those that partition. Matter can also be split up into substances. Substances are a little bit more pure in nature, but you're going to have to go through a lot of vigor and a lot of changes in pressure, and basically you're going to have to really burn and destroy the substance, which is what we consider pure, into a compound, which in turn, through a lot of very fancy and expensive equipment, gets separated into elements. So substances really are composed of compounds and elements. And then those elements not shown in this flowchart are composed of atoms. And those atoms not shown in this flowchart are composed of protons, neutrons, and electrons. All right, some chemistry now here. Make sure you have a good periodic table handy. The periodic table is like a phone book. It's an ultimate consultation guide. We'll learn how to read a periodic table. There's actually some videos that I posted up that you may want to check out, particularly the one titled Periodic Trend. We have an element, which is what you see in the periodic table. So an element is a substance. Remember, what did we say a substance was? I may have spoken it really quickly, but a substance is something that's very pure. So this pure substance can also be called an element. And an important thing to know is what you see in the periodic table are elements. There are 114 of those that have since been identified. And these elements, or pure substances, cannot really be broken down unless we go through some very harsh, very expensive, high pressure, very high temperature. It's just not biologically or somehow very much earthly possible. By the way, each element is composed of its own number of protons, neutrons, and electrons. So some statistics, there are 114 elements in the periodic table. 82 of them occur naturally on Earth. So some of those are gold. Notice here that gold is an element, but it has an elemental symbol. So if you have a periodic table, you really don't need to memorize the symbol, though if you do it long enough, you'll realize that gold is AU, aluminum is AL. Some of them, like lead, are from the Greek or the Latin, so that element is Pb. Oxygen is actually O, is what you see in the periodic table, but the form of oxygen that we breathe and, quote, natural abundance, unquote, oxygen really is O2. So this brings up an interesting point that I'll talk about later. Carbon is C, and S is sulfur. 32 elements in the periodic table have been man-made. So these are the man-made ones, and we're really not going to talk about them at all. So you don't need to worry about that. So here's some elements in the periodic table and their abbreviations. So notice some of them are not so straightforward. They are derived from the Greek or the Latin. Lead is example. One point I do want to make, the element oxygen that you see in the periodic table is O, but natural abundance oxygen is O2. So even though you see the element in the periodic table, that may not be the most naturally abundant form of the element that's found. Another example is sulfur. Sulfur is actually naturally found as S8. The element doesn't necessarily mean that's how it exists in nature. Continuing on with our definitions, compounds. Compounds are two or more elements joined together. So you don't have any fancy decimals in your compounds. And notice that a lot of these are heteroatoms, so carbon dioxide. O2 or F2, diatomic fluorine or diatomic iodine, those tend to be homoatoms joined together, and they are molecules. So the distinction between a molecule and a compound is that if they're the same atom and it's a diatom or triatom or S8, 8 elements of sulfur joined together, 2 elements of oxygen joined together, then it's a molecule. If it's a heteroatom, such as carbon dioxide or H2O water, then it's a compound. Physical change and chemical change. I use physical change and physical property, chemical change and chemical property, sort of synonymous. They're interchangeable. A physical property or physical change does not alter the composition or identity of a substance, so ice melting. A physical change is something that doesn't really change the chemical nature of that. So Ice melting just becomes water that's in a liquid form, whereas water in a solid form is ice. You can also heat that water and it becomes steam, and that's still water, it's just in the steam state. So really all of these are physical changes, and water still becomes H2O. When you start reacting things or mixing things together and a new chemical emerges, or perhaps a precipitate or solid forms, or perhaps gases evolved, or perhaps a color has changed, then you know that some sort of chemical reactivity or chemical property or chemical change has taken place. So think reactivity when you're thinking chemical property or chemical change. Extensive properties are properties that depend on the quantity or the amount of the substance you're dealing with. So when you're dealing with an extensive property, quantity matters. The amount matters as well. So examples of extensive properties are shown below in this little small table. Mass is an extensive property. Length is an extensive property. And volume is an extensive property. So all of these really, if you're describing, again, we're detectives, we're having to write our observations down. If we are describing matter, if we describe its mass, if we describe its length, if we describe its volume, we are depicting extensive properties of that matter. Intensive properties are those properties that are independent or do not depend on the quantity of matter. So this is quantity independent. So other examples of intensive property that do not depend on the quantity of matter are temperature, color, and boiling point and melting point. But for now, just realize that your classic example of an intensive property is density. So your mass over volume shown here are different substances and their associated densities. So whether you're dealing with 10,000 grams of this substance or 10 grams of this substance or 1 microgram of this substance, the density will always be the same. Gold, whether I have 10 grams of gold, 1,000 grams of gold, or 1 kilogram of gold, no matter how much gold I have, those gold bars I have, its density will always be 19.3 grams per centimeter cubed. Notice the temperature dependence. We usually quote density at a specific temperature. So if I increase the temperature, the density is going to change. It's going to be different. Should also mention physical properties are boiling point and melting point. And that boiling point and melting point are sort of innate. They're physical to that particular substance. The other types of properties, temperature and color, again, it does not matter how much you're dealing with. It's always going to be the same. So the temperature will always be the same. That is another example of an intensive property. 10 grams of water will be at 25 degrees. 10,000 grams or 100,000 grams of water. 1 mil of water, 100 mils of water. Enough time, it will get to 25 degrees. So temperature is intensive property. A little bit of a segue. There are different units of temperature: Kelvin, centigrade, and Fahrenheit. So here are the different conversions to go from Kelvin, from degrees C given Fahrenheit, or from degrees F given centigrade. Kelvin is something you're going to deal with a lot in this course. A lot of equations in Chem 2 will require you to convert to Kelvin. Also, gas laws, all your gas laws are going to involve conversions to Kelvin. So these are just different scales. Okay, notice the freezing point of water is 0 degrees C. You put that 0 degrees C into this equation, and you will get 32 degrees F, which is the conversion from Celsius to Fahrenheit. And 0 degrees C using this equation gives you 273 Kelvin. Notice you cannot go negative in Kelvin. You can go negative in Celsius, like minus 10 degrees C. You go negative in Fahrenheit, minus 10 degrees F. Cannot go negative in Kelvin. Kelvin only has a positive attribute. So all of these equations are temperature conversions, and you will be given these equations on the exam. So any type of temperature conversion will just require you to properly use the right equation to get to the right temperature units. So do not memorize these. They will be given to you on the exam. All right, the final intensive property, I should say, is color. This is an intensive property, not an extensive property. Color. So color, regardless of how much quantity you have, it will be the same color. Okay, 10 grams of sodium chloride will still be white. 10,000 grams of sodium chloride will still be white. So physical changes do not change the elemental identity, do not change or create new products. So essentially, no products are being made from the reactants. So when you're cutting, blending, slicing, shearing, boiling, melting, sublimating, going from a gas to solid, here you're not changing anything in terms of the chemical. If you're doing all of these four things to water, it's still H2O. Grinding, mixing, chemically, anything that's not being made is just a physical transformation. Chemical transformations or chemical properties involving burning, rotting, cooking, rusting. You look at change in color. Okay, now we're looking at observations. Formation of bubbles usually involve gas evolution. Any type of odors. Also, is your test tube warm? Has your test tube become cold? Does a solid form when you mix two chemicals together? All of these imply reactivity. All of these are chemical properties or chemical changes. Intensive properties, remember, do not depend on the amount you're talking about. Density is the classic example. We already also went through some of these other intensive properties. Remember the different units with regards to temperature, degrees C, degrees F, Kelvin. You'll get those conversion equations on the exam. Extensive properties, when we're doing our observations, documenting and writing what we can in our notes. Mass, volume, and length, if we're using those descriptors, we are dealing with or talking about the extensive properties of that matter. The next unit here is very important, base units. The SI base unit for length is meter. Here in the United States, we use SI. I think in Europe, they use the metric system. So these are the base units. Length is meter. That doesn't mean we describe everything in terms of length in meter. We can describe it in terms of feet. We can describe it in terms of yards. We can describe it in terms of inches. We can describe it in terms of mile. But the SI base unit is meter. The SI base unit of mass is kilogram. That doesn't mean we describe everything in terms of mass, in terms of kilogram. We can describe things in terms of pound or maybe a stone. The SI base unit for time is second. We do not have to describe everything in life in terms of seconds. We can describe things in terms of minutes, hours, days, months, centuries, even years and millennia. However, the SI base unit of time is seconds, abbreviation S. Kelvin is the SI base unit of temperature. That does not mean we have to talk about all of our weather readings or our heat or cold evolutions in terms of Kelvin units. We can just as easily describe them in degrees C or degrees F. However, the SI base unit is Kelvin, and its symbol is K. Probably the most important of all of these is the mole, and that is the base unit that describes the amount of substance. MOLE is the name of the unit. The symbol is MOL. So get acquainted with this term here, the fifth term. We have four definitions of the mole, and we'll talk more about that in later chapters. This is the heart and soul of chemistry. And another important one, the SI base unit of volume is the liter. And because it's the heart and soul of chemistry, recognize that MOLE is the symbol, is the unit, MOLE is the unit, the symbol is MOL, abbreviation mole. Prefixes used in SI units. So this should not be hard. Tera is 10 to the 12 as an example. So what does that mean? So we all use computers. We have bytes. Our computer or our hard drive or our RAM could be 10 terabytes, okay, which is nothing more than 1 times 10 to the 12 bytes, okay. We could have 1 gigabyte, which is 1 times 10 to the 9 bytes. So in computer parlance, this kind of makes sense, but don't have to use bytes or you don't have to use computer lingo to describe. Just talking about orders of magnitude. All right, so megameter, you can have a megabyte. Okay, you can have a megaliter. You can have a megamole. You can have any type of these SI base units goes along with any type of these prefixes. Okay, so all of these from tera all the way down to kilo kind of go bigger and bigger and bigger. from the deci all the way down to the atto, you're going smaller, smaller, and smaller. So what do I mean by how to convert? So 1 millimeter is 0.001 meter. But an easier way to state this would be 1 meter is 1,000 millimeters. Or 1 meter is 1,000 milliliters. Or 1 byte is 1,000 millibytes. 1 nanometer is 1 times 10 to the minus 9 meters. Okay, so that's 1 times 10 to the minus 9. So that's 0.00000000001 meters. I probably forgot a zero in there. So that's very, very small. But if I were to ask you 1 meter is how many nanometers, you should recognize, remember your meter ruler, 1 meter is 1 times 10 to the 9 nanometers. 1 liter is 1 times 10 to the 9 nanoliters. So you want to be able to get comfortable in going from back and forth from, let's say, a terameter to a meter, or a terabyte to a byte. Okay? And here they use the SI base unit meter. Okay, well, you can use kilogram, you can use seconds. Let's use seconds here. Okay, I'll pick picometer. Okay, so 1 picosecond is 1 times 10 to the minus 12 seconds. 1 second is 1 times 10 to the 12 picoseconds. So understand these and then understand the symbols, know them. Let's use one more, the mole. Let's beat this dead horse. You're going to use the mole a lot. So in biochemistry, we use micromole. That's how we measure substances in our body. So 1 micromole is 1 times 10 to the minus 6 mole. 1 mole is 1 times 10 to the positive 6 micromole. Right? So like that, we can do the same thing for 10 micromole or 100 micromole or 50 micromole. So let's do some example problems here. The density of mercury, the only metal that is liquid at room temperature is 13.6 grams per mil. Calculate the mass of 5.50 mils of the liquid. You may think you can use the density equation, mass over volume, but I'd like to invite you to do this problem in a different manner. So let's use conversion factors here. This is an intensive property, density. We're given grams per mil, and we have 5.50 mils of the liquid. So how can we convert mils to grams? And we have 5.50 mils, and we know that for every 13.6 grams, there is 1 mil. And with that wonderful conversion factor, which is density, so yes, that's a relationship, the mils cancel, and we are left with an answer 74.8 grams. Notice the mils and mils cancel, and also notice that I put a unit by my number. So always put a unit by that number. Okay, a number without units is meaningless, and that's just bad science. It's bad chemistry, bad biology. All right, now we talk about significant figures here in this part of chapter 1. I have a video that goes through several problems that involve significant figures, so do check that out if you have time. It will give you additional practice. Couple of points here with regards to sig figs, a couple of rules. The first rule is that if you do not have a zero, then you're fine. So 1.234 kilograms is 4 sig figs. And it's only when the rules come in hand is what to do with the issue of zero. So that's really the only problem with sig figs. You may also want to wonder why we have to do significant figures. It's because when you do a math problem or a chemistry problem or an engineering problem, you don't want to write your answer to 16 decimal places or 8 decimal places or however many decimal places. That's just to a point it becomes useless. All those decimal places, the 8th and 9th, 10th place, they become trash, as one of my professors used to tell me. So it's very key that you follow a specific set of rules and principles so that you put in just as much significant digits that you can put while also introducing one digit of uncertainty. If you don't have zeros, just count the digits. Zeros between non-zero digits are significant. So you see that enclosed zero. The enclosed zero over there implies that that zero is, say, So since it is sig, it has 3 sig figs, 3 significant digits. Another point is that zeros to the left of the first non-zero digit are non-significant. So 0.08 liters has one significant figure. So this 0 and that 0 to the left of the decimal is not significant, and to the left of the first real digit is not significant. Right? So make sure you know that rule. There's something called the Atlantic-Pacific rule that sort of makes this kind of easy. If a number is greater than 1, then all zeros to the right of the decimal point are significant. So 2.0 milligrams is 2 significant figures. Okay, 2.0 milligrams, that's 2 times 10 to the minus 3 grams for the mix. Let's go back here and add a 0. If I add a 0, how many sig figs do I have? Okay, it's to the right of a real digit, so this will have 2 sig figs. If a number is less than 1, then only the zeros that are at the end and in the middle of the number are significant. So at the end and in the middle, all right? So 0.0420, right? This is definitely significant. This is significant. And this to the right is also significant. This has 3 sig figs. So if it's to the right of the decimal point, and if it's to the right of a real digit, then it's significant. If you draw a map of the United States of America, here's the Pacific Ocean, and here's the Atlantic Ocean. So P Pacific means decimal present. Okay, once again, P Pacific decimal present. So that number whose significant figures you want to attest to has a decimal point. You're going to go from Pacific to Atlantic. That is, you're going to read from left to right. If that number whose significant figures you need to report is not with any decimals, that is decimal absent, you're going to start from the Atlantic and read from the Pacific. So then you're going to determine the number of sig figs going from the right to the left. So let's take a look at an example here. So the number of sig figs in the following measurements, 478 centimeters. So this does not have a decimal, so is decimal absent. We're going to read it from here to here, from Atlantic to Pacific, or from right to left. But you know what? There's no zeros here. I don't have to worry. It's going to be 3 sig figs. 6.01 grams. Atlantic or Pacific? Well, the decimal is present. So we're going to read this from left to right. 6.01, Pacific to Atlantic, decimal present. So 6.01, we're going to go 6.01. That should have 3 significant digits. All right, that is an enclosed 0. 0.825 meters. All right, decimal present. So we're going to read from Pacific to Atlantic, left to right. So is this 0 sig? The answer is no. Okay, anything to the left, especially if it's 0, is not sig. But this 8 is a real number, so that's sig. Sig means significant. This 2 is sig, that's significant. And this 5 is sig, that's significant. So just like the other ones, this has 3 significant figures. 0.043 kilograms, decimal present. So we're going to go from left to right. Pacific, decimal present. Atlantic, decimal absent. In this specific problem, the decimal is present, so we read it. Is this 0 sig? The answer is no. Is this 0 sig? The answer is no. Generally, zeros to the left are not sig, and this will be 2 sig figs. The 4 and 3 are definitely sig, significant. All right, exponents, 1.310 times 10 to the 22 atoms. This is as easy as pi, so anytime you see something that's expressed as an exponent or scientific notation as shown, all you got to do is just read the number of digits to the left of the exponent. So here we have 1, 2, 3, 4. This is going to be 4 sig figs. Okay, so if I'm a test taker and I see a number that is an exponent form or has something that's expressed in scientific notation, I'm very, very happy. And the reason why I'm very happy is because all I got to do is read or recite the number of digits that are to the left of the 10 or to the left of the decimal, and that's 4. So this is 4/6. All right. So what is this? All right. So this is actually a little bit tricky, and I'm not going to really test you in terms of an exam on this. But this, you may think it's 4/6 figs. And you're right if you thought this was 4/6 figs, but the decimal is absent. So because the decimal is absent, you can read it going from right to left. And this going from right to left means that 0 may or may not be significant. This 0 may or may not be significant. This 0 may or may not be significant. Well, we know this 1 can be significant. So the answer here is that this is ambiguous. This could be 3 sig figs. This can be 2 sig figs. This could be 1 sig fig. All right. So it's ambiguous. To remove my ambiguity, this is ambiguous. So to remove that ambiguity, and if I wanted in 4 sig figs, I would use scientific notation. Or if I wanted in 3 sig figs, I would do 7.00 times 10 to the power of 1. 2 sig figs, I would use 7.0 times 10 to the power of 3, and 1 sig fig, 7.7 times 10 to the power of 4. So if you want either 4, 3, 2, or 1 sig fig, you have to use scientific notation to get the specific amount of significant digits. So that's tricky when you're dealing with whole numbers or numbers without the decimal because there is ambiguity. We know the 7 is definitely sig, but the question is, when we report 7,000 mils, did we round it off? And how did we round it off? Did we round off this digit? Did we round off to this digit? Or did we round off all the way to these digits? We have no way of knowing. So this could be either 4, 3, 2, or 1 sig fig. Use scientific notation to get the right number or the specific number of sig figs. How do we do math to the right number of significant digits? So for addition and subtraction, look at the decimals, and the least number of decimals is going to be the number of decibels you report in your answer. So as an example, 89.332 plus 1.3, how many decimals are here? 3 decimals. How many decimals are here? 1 decimal. What should the answer be reported to? Well, it can't be reported to 3 decimals. Why cannot? Why can't it be reported to 3 decimals? The reason why it cannot be reported to 3 decimals is because you only know the value of this number to 1 decimal. So you report this to 1 decimal place. So what about this one? How many digits should this answer be reported to? This has 4 decimal places. This has 3 decimal places. So really just should be reported to 3 decimal places. How do we deal with sig figs when we're talking about multiplication and division? Again, we're going to use what's called the weakest link. This time we're not looking at the decimals, but we're looking at the actual number of sig figs. All right, so the original number with the smallest number of significant figures, that's what you want to report. All right, so looking at 4.51, we're doing multiplication and division now, not addition and subtraction. This is multiplication and division. This has how many sig figs? Okay, this has 3, and this one has how many sig figs? 6. So 3 versus 6. And what is the weakest link? The weakest link is 3, so we're going to report this to 3 sig figs. So this is not the right answer. 3 sig figs would be 16.5 for me. Okay, I'm not going to round up. What about this one? Division. 6.8 has 2 sig figs. We're dividing it by 112.04. That has 5 sig figs. So 6.8 divided by 112.4. The final answer should be 2 sig figs. That's the weakest link. So rounding this off to 2 sig figs, 0.0606926, that's 6, pushes this up to a 1. I would say to get this to 2 sig figs, I will report it as 0.061. One thing I do want to mention is that if you have a combination, addition, subtraction with multiplication and division, okay, look for parentheses. All right, you want to work your way out from the parentheses. First work the inner parentheses and then work the outer parentheses. We don't have examples like this shown in this example problem set. However, we will have some in the YouTube video that's also attached to this Blackboard module. So get some practice doing that, and I also think your homework problems will have some additional practice doing these as well. So these are the answers that I got when I did these. You can check them with your tabulations. Again, homework practice problems as well as that video that I've uploaded in the Blackboard. Try to differentiate between accuracy and precision. You need replicates. You need more than one trial. Okay, so that's why in science, more often than not, we do duplicates. Best to do triplicates. But if you do more than triplicates, obviously you're raising your chances at accuracy and you're raising your chances of being precise. Ability of those replicates to be reproducible as well as to hit a target. So to best describe accuracy, accuracy really is, in the dartboard example, is hitting the bullseye. Okay, if you're really accurate, you're getting to the right spot, or you're getting to where you want to be, or you're getting to that designated number, or that designated value, or that designated pH, or whatever measurement metric you want to study. Precise is basically, again, we're talking about metrics, is you may not hit to your threshold or your goal or that right pH or that right temperature or that right mass or that right molecular weight if you're trying to do some drug discovery, but by golly, you're reproducible, and that also is pretty good in science if you're reproducible. Situation on the left, okay, is this particular dartsman accurate or precise or both? And I would argue he's both, okay, because he's pretty reproducible at hitting the target. The target is the bullseye. So accuracy is really getting your target, whatever observation or whatever standard or whatever metric that may be. Again, in the dartboard example, it's the bullseye. Precision basically is reproducibility, getting there, getting that same number, getting that same pH, getting that same temperature, getting that same molecular weight. Again, replicates, we have to do these observations, we have to do these experiments multiple times. Otherwise, accuracy and precision, they don't work with n equals 1. What would you say, accurate or precise? Probably precise but not accurate. Okay, this is accurate and precise. This is precise but not accurate. And what about this third one? Okay, neither accurate, neither precise. I want to close chapter 1 with some dimensional analysis problems. Relationships, relationships, and relationships. That's going to be the key. Person's average daily intake of glucose is 0.0833 pounds. Okay, the SI unit of weight is kilogram, not pound. But that's okay. We use pounds all the time in our everyday language. But what is this mass in milligrams? Okay, so we're going from a metric unit, pound, okay, to SI, grams, but not kilograms, but we're going to milligrams. All right, so obviously we need a conversion factor here, and thankfully we have this conversion factor given to us, 0.0833 pounds. And what's our conversion factor? Our conversion factor is 1 pound. So I'll put my pound here because I wanted to cancel. 1 pound is 453.6 grams. So nice thing here is that this pound is going to cancel out with that pound. So let's go ahead and cancel these pounds out. Okay, with the pound canceled, we're left with grams, which is what we want. Actually, no, that's not what we want. We want it in not grams, but in milligrams. So we need another conversion factor here. So that conversion factor, and let's go ahead and cancel out the grams. So this gram is going to cancel out with this gram. And now we're left with milligrams, which is really what the problem is asking us for. I would probably use 3 sig figs. Okay, this is ambiguous. This is 4 sig figs. This is 3 sig figs. I'll be more clear on an exam in terms of how many sig figs or how many decimals to use. And doing that math, I will get an answer of, so when I do this, I get an answer of 3.78 times 10 to the 4 milligrams. Again, notice I put units. I can also do this another way. I could have this be 1,000 grams equal to 0.001 milligrams. An average adult has 5.2 liters of blood. What is the volume of blood in meters cubed? So with that conversion factor, and these types of conversion factors will be given to you on an exam to help you with the cancellation of units. So given this conversion factor, I should be able to successfully do this. So is 2.54 centimeters cubed. And what do I need to do next? All right, so I know that for every 100 centimeters, there's 1 meter, but I have to cube it because I need my answers in meters cubed, not meters. So by cubing this conversion factor, I get meters cubed, and the centimeters cubed cancels out with the centimeters cubed, and the liter cancels out with the liter. So doing this math, I get this as the answer. I decided to go to 2 sig figs from that 5.2. This one's 2.54 is at 3 sig figs. The density of a liquid at its boiling point is minus 196 degrees C, or 77 Kelvin. And at that temperature, its density is 0.808 grams per centimeter cubed. Okay, don't forget we quote a density at a specific temperature. Convert the density to units of kilograms per meter cubed. So what are we being given? We're given this density. And what are we being asked? We're being asked to convert it to this. So let's go ahead and start with what we're given. This is the density we're given. We want to convert it to a new density with different units. So we want to convert it to kilogram per meter cubed. So we know that 1 gram has 1,000 kilograms, or you can say 1 kilogram has 0.001 gram, same thing. And now I got my grams and grams canceled. And then my next conversion factor is to convert the centimeter cubed to meters cubed, all right? So we know that I got to do something else with this, and what I have to do here is I got to cube it. So if you guys know the reason why we have to cube this, the reason why we have to cube this entire thing is that 100 centimeters cubed cancels out with the 100 centimeters cubed, and the meters cubed stays in the denominator, and the kilogram stays in the numerator. So when I do that math, I get 8.08 times 10 to the 8 kilograms meter cubed. This last problem is an interesting problem because it introduces us to relationships that we probably have not encountered before. And if all of the above seems familiar or relatively easy, I predict that this problem, even though it deals with something called a mole, and you may not know what it means, but that's okay. This problem also should be easy because it's along the lines of the same problem. Remember, relationships, and relationships. So the molecular weight of hydrochloric acid is 36.01 grams per mole. How many grams are there in 0.25 moles of HCl? So what are we given? We're given that we have 0.25 moles of HCl. And what are we asked? We're asked how many grams. Well, what is the conversion factor given to us? This is the conversion factor given to us, 36.01 grams per mole. So without even knowing what a mole is, or maybe having a little bit of a clue what a gram is, you can still solve this problem. We have 0.25 moles of hydrochloric acid, known as HCl. That's its chemical formula. That's what we're given. And we know that for every 1 mole of HCl, there's 36.01 grams of HCl. Well, I may not know that, but I was given that. So the mole HCl and mole HCl cancel, so I'm just going to cancel those out here. So doing that problem, I get 9 grams of HCl. I went to 2 sig figs, 0.25. Right, so this thing here in the middle is a conversion factor. It's another relationship. It may involve a unit, mole, that you have not encountered before or may not know much about, but we still were managed to successfully tackle this problem. Molarity. So this has units of m, and the m means moles per liter. Okay, so you may not know concentration, and you may not know that molarity is an expression of concentration, but we're in Chapter 1, we know unit conversions, and we know about relationships. So how many moles are in 25 mils of 0.25 m, molarity HCl? Well, what does m mean? Think about it. What does m mean? All right, the answer is right here. The m also means moles per liter. Probably don't know anything about molarity yet, but we know enough to cancel out our units. So what are we starting out with? What are we given? We're given 25 mils and 0.25 moles per liter. So moles per liter, that's not what I started out with. I started out with ml, mils. So yeah, I better convert that to liters. And now we know that for every 1 liter, every 1 L, we have how many moles? We have 0.25. Again, how do I know 0.25 M, big M, is 0.25 moles per liter? Because the problem tells me that. The M also means moles. Doing that, 25 times 0.25 divided by 1,000 should give us 63 moles of HCl. All right, so you may not know anything about molarity. However, you should still be able to solve this problem. What about part C? How many grams are in 25 mils of 0.25 molar HCl? So how many grams of HCl are there in 25 mils of 0.25 molar HCl? Well, how will we do this problem? All right, well, I'm going to copy and paste this. Okay, why do I copy and paste that? Because I know this tells us how many moles are in 25 mils of 0.25 molar HCl, but how many grams are there? All right, so what is that conversion factor? Okay, well, look at that part A. What is the conversion factor for hydrochloric acid? Okay, it's right there. So for 1 mole of HCl, we have 36.01 grams of HCl. Let's look at our units here. All right, the mils and mils cancel, the liters and liters cancel, and finally the moles and moles cancel. So now we're left with grams of HCl. So this is a conversion factor given to us in the problem. And this is a conversion factor given us to the problem once we decode that big M molarity stands for moles per liter. So doing that math, 25 times 0.25 times 36.01 divided by 1,000 should give us the right answer. When I do that, I get 0.23 grams of HCl. I decided to go to 2 sig figs because of that 25 as being 2 sig figs as being the weakest link. I'll be more specific on the exam in terms of decimals and the number of sig figs to report. So that is the completion of chapter 1. Do the practice problems, or the practice homework problems, check your answers. Any sort of quandary, any sort of problem, any sort of issue, check the YouTube videos that are also posted on Blackboard according to pertinent topic. And of course, if you're stuck, you can always come email me or see me when I come back.